looking at proving something by induction, and to prove for this that it is divisible by 3, we could go, oh, what if n was 1? So 4 to the 1 is 4 plus 2, 6. Hey, that works. 6 is divisible by 3. What about when n is 2? 4 squared is 16, plus 2 is 18. Yep, that works too. What about 3? 4 to the power of 3, 64, plus 2, 66 is divisible by 3. We can keep going. But is that a good enough proof to say that that will work for all values of n? No, because you can't just pick and choose the things. You've got to say it's proof for all. So, and by the way, just to satisfy my curiosity, do you remember what this means? Good. So this, z, is an integer. So it means a whole number. And of course, it's greater than 0. So we're talking about positive integers. Why they didn't actually write with a plus there, but anyway, they like to write it like that. But we're talking about positive whole numbers. Okay? So, in order to do it, we're going to do this thing where we go, if we can assume that it works for a particular value, and if we assume that's true, if we can prove that it then works for the next one, it's like a dominoes. So if I can prove it works for this value and then the next one, well, if the first value was 1, then it would work for when it's 2. If it works for when it's 2, then it would work for 3, because I've then proven it works for consecutive values. That's the gist. So what we do, and I'm going to write the stuff in green that is mandatory. The rest you sort of go in by thing. So this is for divisibility. So the first thing you have to do is you have to write your original statement for all n. So what we're wanting to do is to prove that 4 to the n plus 2 is divisible by 3. So we're going to say equals 3a, where a is some integer. Okay? Does a have to be a positive integer? No, not really. But it has to be an integer. Right? So it has to be 3 times a whole number. If it was 3 times, I don't know, 2.2, then it's not divisible by 3. Are we happy with that? Okay, now for this one, it's got greater than or equal to 0. So we have to then start by proving P of 0 is true. If it had n is greater than or equal to 1, then I would start with P of 1. If it had n is greater than or equal to 2, then I'd start with P of 2. And so we pop in, wherever n is, we're going to replace it with 0. So I'm now just following along. We go P to the 0 plus 2. What is anything to the power of 0? 1 plus 2 equals 3. Therefore, P0 is true. Keats, yep. Okay, this is where you're having a little bit of trust in me and it will come to, we're going to assume. So remember we said we couldn't go, oh, let's try n is 0, n is 1, n is 2, n is 3. That's no good, right? So what we're going to do is we're going to assume for any value, and instead of saying n, hold on to your horses, but we are going to introduce another value. We're going to assume pk, and I have a thing of putting the brackets around. You can just say pk if you wanted to. Assume pk. We're going to assume that pk is true. What does that mean? This is where we're going, well, pk, k could be 1, it could be 5, it could be 7, it could be 8, whatever. We're just going to assume it's true. And so what that would mean is that, that didn't work. It means 4 to the k plus 2 will equal 3a, where a is any integer. So we're going to assume that this is true. We're then going to, this is the bit, the only maths we're really going to do, we're going to assume or prove that the next term would also be divisible by 3, right? So we're saying if k is divisible by 3, and we can then use that to prove the next term, so k plus 1 is divisible by 3, that should mean it's divisible for all values, because k could then be 2 and then 3. And if k is 3, and then 4 would be divisible. And then if k was 4, well, 5 would be, like, it just keeps going, and it proves it's the domino effect, they call it. I'll show you in the book in a minute. All right, so to prove pk plus 1 is true. So k plus 1, all we do is wherever k or wherever n was, we're going to replace it with k plus 1. So we go, we want to prove that 4 to the k plus, oh, I should have left a line. Oh well. 4 to the k plus 1 plus 2. And what we're trying to do is we're going to try and show that this is 3 times something. Right? First time you do this, but once you've done it once, you'll see it's a pattern and it goes all the way. So how do we do that? I'm glad you asked. Here we go. We want to, remember what we said, we want to assume pk, so we want to use that. How can I use this when it's not even in here? This is a 4 to the k plus 1. I've got a 4 to the k. Yep, I'm going to separate this. So I'm going to go 4 times 4 to the k plus 2. Would you agree? Because when I'm timesing by the same base, you add the powers and that would give me this. Yes? And now I am going to use this and I'm going to substitute it in. So this becomes 4 times, now what is 4 to the k? Is it not 3a take 2? Uh-oh. Someone asked, do you have to put using pk? Yes, yes you do. Oh, Felix doesn't like it. It's going to, like, this is a step-by-step locked-in process. Okay? So as I said, everything that I'm writing in green, those are mandatory. They are going to be there for every single question that you do, regardless of if it's divisible by 3, 4, 5, 6, whatever. Okay? All right. Guess what? You are nearly done here, people. Expand your brackets. 4 times 3a. Now, this is a part of the topic where you can do this not using a calculator. I get, 4 times 3 is 12, but sometimes it might be 17 times 27 because you're trying to prove that it's divisible by 17. So I would get into the habit of just going, keep that as 4 times 3a, because you're going to eventually want to pull out that common factor of 3. You could ignore me, that's fine. 4 times 2 is 8, plus 2. Hopefully you're getting a little bit excited at this point. Yes? Because what can you now do? Remember what you're trying to do? You're trying to prove that it's divisible by 3, which means you eventually want to say it's 3 times something. So can you pull out a factor of 3? Yeah. So it's going to pull out that factor of 3. It means it's 4a take 6, right? Because this is an integer, as a is an integer. Got a little bit excited there. So thank you, people, because that should be 2. That's how exciting it gets. Right, now the love and the joy doesn't end there. So far, you've done a brilliant job, but this is where mathematicians are really picky, and you have to actually summarize and say what you have done. And at this point, I'm going to show you, it's this statement that you have to put at the end every single time. Now, very often students will groan and go, oh, do I have to remember that? It is basically just summarizing the process. Since P of naught is true, isn't that the first thing that we proved? So since that was true, and we proved that pk plus 1 is true whenever pk is true, therefore pn is true for all. So it's basically summarizing what you did. That's it. Do you have to write it every single time? Yes. But you might find me sometimes writing ish. Insert statement here when I get lazy. But today, for our first one, we're going to write it. So what was the process? We said that, yep. So let's not even look at the book. Let's see if we can remember what our process was. Since, first thing, P naught is true, and pk plus 1, right, when pk is true, this is what, then pn is true for all n greater than or equal to 0. Okay, and that's why at year 12, because this is a topic in year 12, the markers were really grabbing people and going, do you know what, if you don't actually write the PN statement, then this statement is no good, because what is PN? So you need to make sure that right at the start there, you had your PN. I guess I should have put up here for n greater than or equal to z. All right? Now, you're going to do similar things over and over again. What kind of things are you going to have to do? We're going to start question 3. So again, we're going to do 1 divisible by 3. There's a bit of a warning on this one. We'll do it together. That's probably the hardest one. Then we've got, or is it B? Might be B. Divisible by 6, divisible by 12. It gets a little more complicated when we have crazier expressions that you want to show are divisible. We're going to go 5, 11, here's 1, 17. Right? I don't know about you. I don't know my 17 times tables. So that's where we use some of those tips where you shouldn't have to use a calculator. Anyway, we'll see how it goes. All right. So 20 minutes. I reckon we can get a fair chunk done. These, we are going to get into good habits to do, but maybe a little bit later on we might start skipping a few steps because we just want to experience and do a lot of the maths, because you'll see a lot of it is just rewriting things. Same thing over and over again. All right, so 3A. You can write your statement. Okay, all positive integers. This is the debate. All positive integers, does that include 0? No, we're going with 1 or more. So you could write it as n is, I like to do that. You could just say n is z and then n is greater than or equal to 1, whatever. Floats your boat. I prefer the top one, less writing. Okay? All right, so everything in blue is a must. P1, and then, I guess that shouldn't be in blue, but anyway. Are we okay out there? So you're going into the routine, wherever n is, replace it with 1. So it's 1 cubed plus 2 times 1. So I get 1 plus 2 equals 3. Therefore, P1 is true. We just said what comes next, and people were already right into it. So we're going to assume PK is true. And so wherever n is, we replace with k. So we're going to go k cubed plus 2k I sometimes leave a line because I can rearrange my PK. Like before, with the one that we did over here, oops, went too far. Sometimes I leave a line. I would have said 4 to the k equals 3a take 2, and then it's easy to see and substitute. You might go, I don't need to leave a line to rearrange. You'll see sometimes they get a little bit more complicated. Anyway, and by the way, there's nothing stopping you. You could replace the 2k, so you could have 2k equals 3a take, or you could have the 3a and substitute. There's different ways that you can do it. I just have the one. I like to stick to it. But anyway, creature of habit. All right, so I'm leaving a gap just in case. So to prove pk plus 1 is true. When I say is true, we mean it's divisible by 3. All right, so what do we have to do? We go back to our original statement. Wherever n is, we now want to replace it with k plus 1. So this is a little bit uglier, so it becomes k plus 1 cubed plus 2k, and we're going to play with that to see, can we get it to equal 3 times plus 1? Can we get it to be 3 times something? I have to rewrite that. Okay, so what can we do? We have to do something. Exactly. They said expand. Normally, k plus 1 we'd go, ew, but we remember Pascal! Right, just turning the aircon off because Joe is looking freezing over there. Pleasure, Joe. Okay, so that becomes 1k cubed plus 2k squared plus 3k plus 1. If you want a tutorial on Pascal, let me know. Yep. Probably not today, next lesson. I would have thought you would have gone over it when you did first principles. All right. Now, we watching? Oh, I don't know. I do know because my ear's blocked and there's lots of chatter. Anyway, carry on. 1, 3, 3, 1. I even wrote 1, 3, 3, 1. Sorry, peeps. So at this point, you've got options. I've had people before, they've replaced the 2k using this. Rearrange, 2k equals 3a, take k cubed. I always just use the worst one and I rearrange. So I'm looking at this, I'm going k cubed equals 3a, take 2k. Agreed? So where that appears, I'm going to sub it in here. So I now have, instead of k cubed, I'm going to say that's 3a minus 2k, and then I've got all the rest. So 3k squared, 3k plus another 2k is 5k, 1 plus 2 is 3. I'm changing colour. Why? To say I have used PK. Whenever you do that. And normally every year I forget. So it's someone's responsibility in the class to remind me. Who shall it be? Lamb, I crown you. I crown you the reminder. All right, here we go. What are we hoping to find? Multiples of 3 when we simplify. We've already got the 3a. That's groovy. Oh, 3k squared. I'm happy there. What's what's minus 2k plus 5k plus 3? Isn't this a bit like first principles when you know, find that h's all cancel? And so we go, that's 3a plus k squared plus k plus 1. That's an integer. Therefore, pk plus 1 is true. Now, I know the statement. You need to write it down.